Okay, we're going to continue on here, chapter 16, I think. We're not too far to the end here. So last time we talked about several things. We talked about our delta S of the universe, which is again our delta S of our system minus the delta S of our surroundings. Remember that if we calculate delta S of the universe there and it's greater than 0, then we do have a spontaneous process happening. This is essentially our products minus reactants in terms of how to calculate it. Our surroundings is our minus delta H of the reaction divided by the temperature in Kelvin. Remember, as we talked about, this is the one that does have the negative symbol in there. We talked about Gibbs free energy, which are several different sort of Gibbs formulas. You could calculate delta G of the reaction, just like all other thermodynamic type properties, by taking the products minus the reactants. Remember that when you do so, as we talked about, you want to make sure that you do look it up in the correct state. You also want to make sure that you do multiply by the coefficient in the equation. To do that, we can use delta G to predict spontaneity, and if delta G is negative, that usually means the reaction is spontaneous the way it's written. If our delta G is positive, it's going to be non-spontaneous the way it's written. R would become spontaneous if you reverse the reaction, which would essentially make your reactants your products your reactants, and the sign would basically change in that case if it was non-spontaneous. We also saw a delta G formula where you can use delta H minus T delta S. So if you have the enthalpy and entropy sort of given to you, you could use this formula here to also calculate the delta G. Remember that we do have unit issues here that going to be in kilojoules, that typically in joules. So once again, you do need to do some type of conversion there to make sure everybody's in the right units and everything sort of cancels out correctly. We also talked about sort of non-standard conditions where we have delta G is equal to delta G naught plus RT natural log of Q. This being our delta G under standard conditions. And remember, you see that little knot, it usually does mean sort of table conditions, which is 25 degrees Celsius, 1 atmosphere in terms of pressure, if you're talking about any type of gases, and 1 molar in terms of concentration, if you're talking about any type of concentration. Q is our reaction quotient. So just like normal, that's going to be our products over our reactants, calculated the exact same way as we calculate K. T is our temperature in Kelvin. And a reminder that the R here is the gas constant, but it is the 8.314 version of it. So don't use the 1 for the ideal gas law here. So you can kind of think about it as this is what the delta G would be under non-standard conditions versus, kind of standard conditions here. And then again, what that usually would entail is something being not standard conditions. So once again, maybe you got some pressures that they're not all 1 atmosphere, some concentrations, they're not all 1 molar. That is kind of the typical thing. We also related it to the equilibrium constant, where when we're at an equilibrium process, our delta G will equal 0, our Q will become K, and that will give us delta G naught is equal to minus RT natural log of K in this case. So obviously, as we talked about, this is the equation that you would use for the equilibrium constant or anything involving the equilibrium constant. Either you're asked to solve for it or you're given it. You would want to go into this equation here. The nice thing, as we talked about, is in all these cases, a couple of things. We talked about the idea of temperatures relationship here with this equation. So again, the temperature and depending on the sign of H and S, can play a role as to whether or not you would expect, for example, a reaction to be spontaneous or not, depending on, if they're both positive, negative, depending on that situation. We also saw that we could use this equation here if we came across a situation where the reaction was not spontaneous, and we could set it equal to 0. and rearrange that equation and solve for T, solve for T here. And T would be delta H over delta S. That would give us our temperature at which it would become spontaneous, or the minimum temperature at which that reaction would try to turn spontaneous. We also talked about the entropy of vaporization and fusion and sort of phase changes, which is also an equilibrium situation, which also means that you would set that guy equal to 0. And you can solve for S in this case, which would be delta H divided by T. And that could give you something like the delta S of vaporization. That again is the one, as we were talking about earlier, that should not be confused with the top one there, where there is again a negative in there for that reason of the opposite location. Here there is no negative. And that delta H in the case of, say, the delta S of vaporization would be something like the heat of vaporization would be used for that, and the temperature would be the normal boiling point for that particular substance in Kelvin. Any questions on any of that stuff there we talked about last time? All right, so we got a few examples here, I think, to finish it up on. So why don't you give it a go? Calculate the equilibrium constant for the following reactions. Here's some delta G values. So let's take a look. So the key here, as we talked about last time, is really sort of choose the equation that sort of works for what's given to you or what you're trying to find. Clearly here we're trying to find the equilibrium constant, so that should direct you to this equation here, which is pretty much the only one that has the equilibrium constant in it. Doesn't matter what type of equilibrium constant, they're all the same. They're all K values. So in this case, we do have the temperature. R is a constant, so again, that's going to be our 8.314 joules per Kelvin per mole. We're going to convert our temperature here by adding 273 into Kelvin. It's going to give us a 298. We do actually need to calculate our delta G, not in this case. So we will go to the table there, look up the values, and our delta G not here will be our products minus our reactants. So in this case, we will go with our product there, which is 3 times 0 kilojoules, minus our reactants, which is 2 times 163.4 kilojoules. That is going to give us a delta G here of negative 326.8. That is sort of the missing piece that we need there, by the way, based on the delta G. Is this reaction spontaneous? This reaction is spontaneous, right? Because we do have a negative value here, so this reaction should be spontaneous. And we'll talk about maybe what that means in a second. We're going to put our numbers in. I'm going to go minus 326.8. Once again, I'm going to multiply by 1,000 to convert it to joules. You could convert the R to kilojoules if you like, whichever way you want to do it, but they do need to be in the same units. 8.314 joules per Kelvin per mole. And again, why I did convert that to the same units here. Temperature 298, natural log of K in this case. So kind of cleaning up the right-hand side there, 8.314 times 298, going to give us a negative 2477.572 natural log of K equals negative 326,800 joules. We're going to divide this to the other side. By the way, we also want to make sure we take the negative with it to the other side because that's kind of important. So we're going to end up with about, I'll go up here, 131.9 equals the natural log of K. To get rid of the natural log of K, we're going to take the E of both sides. That E will get rid of that and make my K equal. And again, why it's important to make sure you do take the negative to the other side. You'll end up with a 1.9 times 10 to the 57. Yeah. as our K value in this case. Questions on that there? This again should agree. So as we just mentioned a second ago, this is a negative delta G, which means this reaction is spontaneous. This reaction is spontaneous. It should be heading to the product side, and that means I should have a lot more products than reactants, and I would expect my K value to be large in this case, and I would say that qualifies as being large. If you forgot to take the negative to the other side and you take the E of the negative 131, you get a really small value. So these are things you want to think about just in case you forget to maybe carry a negative over. They should agree with each other. Any questions on that there? All right, so let's try another one here. Calculate the delta G naught for the following if the KSP is 1.7 times 10 to the minus 6. Actually, in this case, given the K, so again, that's going to take us to the only one that has K in it, which is this one. In this case, we pretty much have everything on this side, so all we have to do pretty much is plug and chug into here. Also, again, got to convert our temperature there into Kelvin. So doing that, that will give us the delta G minus our 8.314, which is our R, times our temperature, 298, natural log of 1.7 times 10 to the minus 6. Popping all those numbers into there. Will get us here. Looks like 32914. These are joules, by the way. We can divide it by 1,000, which will give us a more common type number here for delta G, which would be 32.9 kilojoules in this particular case. Any questions on that one? Delta G here is positive. Reaction spontaneous or non-spontaneous? What do we think? It is non-spontaneous, yes. And that matches our K value, which is a small K value, right? Which means we should mainly have reactants at equilibrium. So again, those things should sort of agree with each other. And if one doesn't agree with the other, then probably something went wrong there with your calculation. Yeah. Any questions on that? All right, one last one here for the chapter. Delta G naught for its reaction is 2.6 kilojoules at 25. We got some initial pressures of 4.26, 0.024, and 0.23. What is the delta G for this reaction? And which way will it be heading, perhaps? Okay, let's take a look at this one. So we are looking for delta G. They give us delta G naught. By the way, we could kind of think of this as being non-standard conditions, as when we look at our pressures, they are not all 1 atmosphere. So this would be sort of the non-standard part of what's going on here. That brings us to really the only equation that has both of those in it, which is our delta G is equal to our delta G naught. Remember that this one's actually plus, as we talked about last time, RT natural log of Q. Again, we calculate Q just like normal. So we're going to go our products here, which is our HI. We are going to square it because of the coefficient, divided by H2 and I2. And since we're dealing with pressures, it's basically the same thing here. So we'll do the partial pressures of each of these guys in this particular case. So we're going to put our pressures in there to get our Q, and we will get HI, which is 0.23 squared, divided by 4.26 and 0.024. That's going to give us a Q value here of 0.5174. Now, and everything else is pretty much in good shape. Once again, converting our temperature into Kelvin. So our delta G in this case will equal our delta G naught that was given to us. By the way, if it was not given to you, you would have to go and calculate it yourself, like products minus reactants. Again, I'm going to convert it to joules, so I got the right units or the same units going on both sides here. Again, you do not want to keep one in kilojoules and the other one in joules. Plus my R, which is 8.314 joules per Kelvin per mole, which again is why I converted this guy into joules, so we're good there. Temperature 298, natural log of 0.5174. Cleaning up everything on the right-hand side there. We're going to do a little natural log of our guy there. Going to multiply it by 298 and multiply it by 8.314. That's going to get us here basically negative 1632.52 joules to be added to our 2600 joules. So we'll take 2600 plus my negative guy there. Gonna yield me 967 joules, or about 0.967 kilojoules in this particular case. Any questions on that calculation? So under standard conditions, the delta G naught is 2.6 kilojoules per mole. Under standard conditions, is this reaction spontaneous? No. Did by playing with the pressures here make this reaction spontaneous? The answer is no, it's still positive, right? So it made it a little bit better in a sense. I guess it's a little less, but it is still going to be a non-spontaneous process, which means we would predict that the reaction is going to hang out towards the reactant side, right? As it's not going to go towards the products in this case. Any questions on that calculation there? So again, as I mentioned last time, pick the delta G equation that works for the information sort of given to you. Yeah. Any questions on any of that there? Questions on thermodynamics, chapter 16 in the books, they say. All right. Yeah. This equation? Are you asking why it's negative in that equation? Is negative in that equation because really that equation is sort of derived from the one we just used? A natural log of Q. There you go. And because when we're at equilibrium, delta G will equal 0. And because we're at equilibrium, this guy will be K. So to solve for delta G, we take this whole entire thing to the other side, and that's how it becomes negative, basically. Other questions? So I would say that's kind of like a place where sometimes people get into some trouble is with the signs of it, and either putting the negative where they shouldn't, or forgetting to put the negative, or like I said, very common on this one, since most of them are like subtracting and negative. People very commonly want to kind of subtract the back part of this one very commonly. Other questions? All right, that does wrap up chapter 16 then. All right, we're going to then roll into chapter 17, which is some electrochemistry talk. The first part we're going to do probably today, or most of it today, might be review for you. We're going to talk about redox reactions. We're going to talk about what it means in terms of redox reactions. We're going to talk about how you assign oxidation numbers and oxidation states. We're going to talk about how you balance redox reactions in acidic and basic conditions, just to make sure everybody's on the same page. Depends, I guess, who you had for 200 days as to how much maybe you did of that or didn't do of that. So we'll just make sure everybody's on the same page here and just kind of go over it one more time before we get into really the heart of the chapter, which is about galvanic cells and that type of electrochemistry. So we're going to talk about redox reactions, which are basically oxidation and reduction reactions that take place. And by the way, oxidation and reduction reactions, they always sort of happen together. So if somebody gets oxidized, somebody else will get reduced and vice versa. So they're sort of related to each other in that sense that if something happens to one thing, the other will happen to the other. That's also a really good thing about redox reactions, which is you could just figure out one of the things, like what's being oxidized, what's being reduced, then the opposite thing is happening to the other substance. So let's talk about some of the definitions here of oxidation. Oxidation means basically that you lose electrons, and reduction uh, basically means that you gain electrons. And sometimes people remember this with the oil rig. Oxidizing is losing, reducing is gaining. Some people like Leo the lion goes grr. Loss of electrons, oxidation, gaining of electrons, reductions. Again, you can use them both together and not have to choose. So you can just put the lion on the oil rig and he'll go grr, and you'll have them both together. I will say in general chemistry, like we're dealing with here, these are probably your go-to definitions for oxidation and reduction. If you continue on to organic chemistry, I'm sorry, but if you continue on to organic chemistry, there's some other oxidation and reduction sort of definitions that very commonly are used. Another definition of oxidation is the gaining of oxygen as you go from reactants to products, or the losing of hydrogen as you go from reactants to products. And pretty much for reduction, it's the opposite of that. It is the losing of oxygen as you go from reactants to products, and the gaining of hydrogen as you go from reactants to products. So in organic chemistry, we're dealing with a lot of nonmetals, and nonmetals, oftentimes it's a lot easier to sort of look for either the appearance or disappearance of hydrogen or oxygen. But for us, pretty much these two definitions are going to be the key ones here for us, which is the losing and gaining of electrons. Now, when things lose and gain electrons, we oftentimes will look, as we'll talk about, at the oxidation number or the oxidation state of a substance, and that is different than the charge that we normally think about in certain situations on a element in an ion. And when you get covalently bonded, it's a little bit different. So there's a really easy way to figure out what is being oxidized and what is being reduced. And the easy way to figure that out is just a basic number line. And zeros there. You got positive numbers to the right and negative numbers to the left. And when somebody loses electrons, they do become more negative or more positive when you lose electrons. When you lose electrons, you then have more protons, right? Which means you become more positive. So if you look at a substance from the left-hand side of the arrow to the right-hand side of the arrow, and its oxidation number is moving in that direction towards becoming more positive, that substance is going through oxidation. Vice versa, if somebody gains electrons, they then typically become more negative because they have more electrons than protons. So if you follow the oxidation number of somebody and they're kind of moving in this direction on the number line towards the negative side, that guy is going through reduction. So that's a really easy way to sort of figure out, what is being oxidized and what is being reduced is by looking at the oxidation states of everybody and figuring out as it goes kind of from the left-hand side of the arrow to the right-hand side of the arrow, how it's changing. And I'll tell you whether or not it's going through oxidation or reduction. Any questions on that there? Now, in an electrochemical process which involves redox reactions, energy is released in a spontaneous reaction, and can be converted to electricity. So as we'll talk about, as these electrons are really being transferred, they could go out and about through a wire and be used to do some type of work like power your device and kind of go back to the other side. Electrical energy could also be used to cause a non-spontaneous reaction to occur, which we'll talk about at the end of this chapter, which is sort of what happens in electrolysis, where you kind of help a non-spontaneous reaction occur by applying some extra energy to do so. So if we look at this reaction here, which clearly I just wrote all over, so let me erase that. So if we look at this reaction here, this magnesium plus oxygen makes a little magnesium oxide. That's the classic burn some magnesium ribbon, but don't watch it as it's burning to observe what happens because it's very, very bright. If we look at what's happening here, one of the things that you should know, or we will talk about, is anything in its natural state that is uncombined has an oxidation state of 0. So magnesium here and oxygen here will both have an oxidation state of 0. It's only when the magnesium, the oxygen get together, they make an ionic compound, and we end up with a +2 for the magnesium. We end up with a -2 there for the oxygen in that particular case. So once again, just to show you how that number line sort of works, if you're not sure in this case, we could look at the magnesium to start with. On the left-hand side, the magnesium is starting at 0, and on the right-hand side, it ends at +2, which means it is going in the positive direction. And that means in this case that the magnesium is going through oxidation. By the way, once determining that, that is all you need to determine, because now you know for sure that the oxygen is going through reduction, but you could do the same thing for the oxygen. Oxygen starting at 0, ending at -2, becoming more negative, and it is going through reduction in this case. We could write half reactions, and this is what is known as the oxidation half reaction. And it is the magnesium going from 0 to +2, giving off 4 electrons. And the electrons here are on the product side, and that indicates that this is an oxidation half reaction. So whenever we have electrons on the product side, it is a oxidation half reaction, like they're being given away. There are 4 electrons. Why? Because each magnesium loses 2 electrons, right? And there's 2 of them, so that is 4 electrons total, right? 2 from each magnesium. Because basically what is happening here is this guy is sending electrons over to the oxygen in this case. The oxygen will then pick up those 4 electrons, and we see the electrons actually on a reactant side, which tells us this is the reduction half reaction, and it will gain those 4 electrons, and each oxygen will end up with 2. These are called half reactions because, frankly, when you add them together, the one thing that should always completely cancel out are the electrons, which are on opposite sides of the arrow. So before you add half reactions back together, they have to always cancel out, and you have to make sure you have the same number of electrons in each half reaction. Sometimes that does require you to multiply a half reaction by a number to get them to the same number of electrons, and then they will cancel out. Everybody on the left stays on the left. Everybody on the right stays on the right-hand side of the arrow. Those 2 guys will come together to make our ionic compound in this particular case. Any questions on that there? That is exactly what we should expect to happen in a metal, non-metal situation, right? Because metals are typically the ones that will lose their electrons, right? And non-metals are the ones that will gain their electrons. That is basically how an ionic compound is formed, right? Metals have all the properties that want to release their electrons. Non-metals have all the properties of, I would like to take your electrons, so thanks for sending them over. And we get a full transfer of electrons, which is what is happening in this particular case. And there we go. Now, if we look at something like calcium here, we could do the same thing. We have calcium all by itself has an oxidation state of 0. Oxygen all by itself has an oxidation state of 0. Calcium ends up with a +2 charge over here. Oxygen ends up with a -2 charge in this case. Once again, we can look at what is happening. Calcium starts at 0, ends at +2, becoming more positive. So it's going through oxidation. Oxygen starts at 0 and ends at -2, becoming more negative, going through reduction. So in this case, the calcium, as we would expect here, is going to give up its electrons to our oxygen, giving us our half reactions there, where once again, the electrons will cancel to give us our overall reaction when we add it together. Now, something being oxidized and something being reduced should also not be confused with two other terms that sometimes come about, which we'll talk about, but I'll just put it here as well. And that is the oxidizing agent and the reducing agent. So the oxidizing agent, the reducing agent are different than what is being oxidized and what is being reduced. The oxidizing agent is always the thing that gets reduced. So the substance that actually gets reduced is known as the oxidizing agent, while the reducing agent is the substance that gets oxidized. The reason those names are like that is because the oxidizing agent causes the oxidation of the other species, because in order for it to get reduced, it has to gain electrons. The only way it could gain electrons is cause somebody else to lose electrons. So that is why it's known as the oxidizing agent. Vice versa, obviously, for the reducing agent. It's called the reducing agent because it's going to lose its electrons, and by that process, somebody else will pick up the electrons and end up getting reduced. So the easy way to remember it is opposite of the name. If you're looking for the agents, oxidizing agent, reducing agent. In this case, the oxidizing agent is which thing? The calcium or the oxygen? It is the oxygen. It is the oxidizing agent. And this guy would be our reducing agent in this particular case. By the way, the oxidizing reagent and the reducing agent are found on the left-hand side of the arrow. On the reactant side is where you find those guys. So that is where you find those two. Any questions on that there? Which is obviously, as I just said there. Now, let's say I had iron 3 chloride goes to iron 2 chloride. Is the iron being oxidized or is it being reduced in this case? Well, if you're not sure, let us take a look at it. FeCl3 means that is iron 3 chloride. That means the iron has what type of charge? +3. Chloride has a -1, right? Right-hand side, that is iron 2 chloride, which means it's +2 and -1. Clearly here, the chloride's just hanging out. It's a spectator ion, not doing much, but it's actually the iron that's changing. And if we just go to our little number line here, iron is starting at +3, which would be over here, and ending at +2, which means it's actually moving to the left and becoming more negative. It is actually being reduced in this case, yeah? So the iron is actually going through reduction in this particular case. And again, that is how you can very simply figure out what is being oxidized, what is being reduced. Any questions on that there? That would mean here the iron 3 would be our oxidizing agent if we had something else with it, obviously, in that particular case. Now, as I mentioned before, there are some other definitions of oxidation and reduction. And like I said, we probably don't use it too much here in general chemistry, but definitely when you get to organic chemistry, like I said, oxygen and hydrogen are a lot easier to sort of follow. So we could use that rule here. For example, if we look at the tin here on the left-hand side, it's got some oxygen. And if we look at the tin on the right-hand side, it no longer has oxygen, which means it has lost oxygen as it went from left to right. That means here the tin would be reduced in this case. We look at the carbon, no oxygen, and some oxygen there on the right, which means the carbon has been oxidized. And because the carbon has been oxidized, it is the reducing agent in this particular case. And it brings about the loss of oxygen in this case. Now, in this case, we actually did have a metal, which means you could actually just look at the metal and sort of figured out what was going on. That is tin 4 oxide, in case you're not sure. That's a +4 in the tin. And that is tin with nothing attached, which means it has an oxidation state of 0, which means if you roll back to your little number line here, the tin is starting at +4, ending at 0. It is moving in a negative direction, which means it is being reduced in this case. So if you're able to still look at the tin and figure out the tin, by default in this case, the carbon would have to be oxidized. Yeah. Any questions on that there? So let's talk about oxidation number, which is also sometimes referred to as oxidation state. And the oxidation number or state is the charge that the atom would have in a molecule or an ionic compound if all the electrons were completely transferred. So as I mentioned before, sometimes the oxidation state or number is the same sort of thing that we normally sort of think about in terms of charges in an ionic compound. But in other times they are not, especially when you're dealing with non-ionic compounds and you're dealing with covalent bonding. So the first rule is what we just saw there. Anything that's in a standard state, anything that is not combined with anything else, will have an oxidation number of 0, basically. Yeah. Normal sort of charges, if you have a monoatomic ion, whatever the charge is on the ion, will also be its oxidation state. I would say in a lot of cases, oxygen is usually involved in an oxidation reduction type reaction. So when you're assigning oxidation numbers, that's usually the best place to sort of start with, which is oxygen. And in most cases, oxygen is going to be -2. The one exception would be if it's really not oxygen, but it is peroxide, like in hydrogen peroxide, sodium peroxide, it will be -1. And how you know in a lot of cases that it is sort of peroxide versus oxygen is those twos there sort of hang around a little bit more than in a normal situation. I would say probably 9 times out of 10 is probably very safe, or even more. They probably assume the oxygen is oxygen and not peroxide. But you do have to watch in case it is peroxide. The oxidation number of hydrogen is going to be +1. The only time that hydrogen will be -1 is really like when it's in the hydride form, which is when it comes after a metal, then it'll be -1 charge. Everybody in group 1 and group 2 will be +1 and +2. Fluorine will be -1. And when you add up all the oxidation numbers, it does need to equal the charge on the ion or the molecule. So if the molecule is neutral, everybody has to add up to 0. And if it does have an overall charge, all the oxidation numbers need to add up to that overall charge. So why don't you take a moment here and let's do HCO3 minus. What is the oxidation numbers for each of those elements there? Okay, let's take a look. So once again, when you have a 3-pack like this, to be honest with you, kind of usually you want to go right, left, and save the one in the middle for the end is usually the good approach there. So I'm going to go with the oxygen, which should be -2. There are 3 of them, which gives me like a grand total of sort of -6 happening there for the oxygens. My hydrogen here is going to be +1, which means I have a +1 situation happening there. Remember that when it's all said and done, it does need to equal the overall charge here, which is -1. So that means in this particular case, the carbon is going to roll with a +4, I believe, and that will give me a -1 overall. Now, when you are saying the oxidation states or numbers, hydrogen should be +1, carbon should be +4, and oxygen should be -2. It should not be like the grand total of -6 or anything like that. Also, when you give oxidation numbers or states, you should keep the negative or positive charge there as well to indicate whether it is positive or negative. So you should not just lay up a number. You should have the charge sort of associated with it as well. Any questions on that one there? All right, so why don't you try some here for each of these guys? give the oxidation states of each of the elements that are present. Okay, let's take a look. We'll start at the top one here. So again, I'm going to start with oxygen. So it's going to be -2. And lithium here is an ionic compound, will be group 1, which will be +1. So lithium +1, oxygen -2 in this case. Any questions on that one? Coming to my one on the right here, fluorine's always -1. And there's 3 of them, gives me a -3. So the phosphorus in this case actually will have a +3 oxidation state or number, and that is +3, and fluorine -1. A reminder that, again, as I mentioned, oxidation states are a little bit different than what we normally associate with charges in an ionic compound. Normally, we think of phosphorus as being a -3 charge in an ionic compound, and that's because he's the recipient of 3 electrons. In this case, it's actually sharing of electrons, and we know between phosphorus and fluorine, which one's more electronegative? It is the fluorine. So when this guy is sharing electrons in this situation, all the electrons are heading away from the phosphorus, and that is what's given it a more positive state due to the unequal sharing of electrons that are happening in this sense. So this is again why we have sort of different oxidation numbers than we think of in an ionic compound when we have a transfer of electrons that's happening. Coming here to nitric acid, -2 for the oxygen gives us -6. Hydrogen is going to be +1. And in this particular case, to get us to 0, that looks like a +5 there for our nitrogen. So same idea here between nitrogen and oxygen. If you were to draw this guy, oops, no, too much. There you go. Again, oxygen more electronegative than the nitrogen, and it's going to draw the electrons away from the nitrogen as they're sharing electrons. And instead of, again, normally what we think of nitrogen as being -3 in an ionic compound, it's actually going to take on a more positive oxidation state in this particular case. Lastly here, -2 for the oxygen. Again, it's a -14. We do need to equal -2, and we do have 2 of the chromiums there. So that means in each case, the chromium is going to be +6. That will give us a +12, and a -14 gives us a -2 overall. So chromium is +6. Oxygen is -2, and over here, nitrogen +5, oxygen -2, and hydrogen +1. Any questions on assigning oxidation states? Really important, obviously, in redox reactions to figure out what is going on, what is being oxidized, what is being reduced. Extremely important when we talk about galvanic cells. So you know which one's your anode, which one's your cathode, what is happening at those sites. So very important to understand that. Any questions on that there? All right, so we're going to also talk about how we go about balancing redox reactions in, say, acidic solutions and basic solutions. These, again, just as hopefully a review for most, but if not, again, hopefully everybody will be on the same page afterwards. Basic redox reactions to balance when we have the half reactions, as we sort of looked at a little bit before there at the beginning. Pretty much all you have to do is make sure you have the right number of electrons in each half reaction and just add them together. And again, if you do not have the right number of electrons, it may require you to multiply one half reaction by a common number. It may actually require you to multiply both half reactions by common numbers so that you could get that. When we're balancing more complicated redox solutions in either acidic or basic conditions, we do balance it through like kind of the water method here. And there's a lot of steps to sort of follow. So let's go through and just to make sure. One of the first things I usually would like to sort of recommend to do is to figure out what is happening in terms of this reaction. So here we have a oxidation state of the iron of +2. As we just saw in that previous example there, +6 for the chromium, -2 for the oxygen, +3 for the iron on this side, and +3 for the chromium on this side. So once again, we can figure out what is happening, for example, here with our iron. Our iron is starting at +2. and ending at +3, which means it is moving in a more positive direction, and that means it is being oxidized. If we look at the chromium here, chromium starting at +6 and ending at +3, which means it is becoming more negative and is going through reduction in this case. So this guy is being oxidized, because they won't always give you that, obviously. This guy here is being reduced, and that means in this particular case, this would be our reducing agent. This would be our oxidizing agent in this particular case. Yeah. Any questions on figuring all that stuff out, which would be good things to know? Yeah. Once you have sort of all that figured out, it's really good. So you can kind of check yourself later on when you're balancing it to make sure you didn't hopefully screw up. The next thing you want to do is split it off into two half reactions. One will be the oxidation half reaction. One will be the reduction half reaction. And to split it off, you basically just pick elements that are the same on each side. So on the left-hand side, I have me an iron. On the right-hand side, I have an iron. Left-hand side, I got something with chromium. And right-hand side, I have something with chromium. So the first thing that you want to do is basically just split it off into two half reactions. The next thing that you want to do is pretty much just balance it like a normal equation. You want to balance all the elements except for hydrogen and oxygen. So then you want to balance except hydrogen and oxygen. So in this case, we would need a 2 here for the chromium, just like a normal coefficient. For the top one, we basically have 1 iron on each side. They just have different charges, but we have 1 total iron on each side. Once you have balanced everybody except for hydrogen and oxygen, then we move to balancing oxygen. And we balance oxygen by adding water. And we add water to whichever side needs the oxygen. So on the top one, there is no oxygen, so we don't need to add any water. Bottom one, there are 7 oxygens on the left, none on the right, which means we do need to add 7 waters to the right-hand side. Now, every time we add water to balance out the oxygens, we are also adding hydrogen. So to make sure that in the end we are not short hydrogen, to the opposite side, you need to add 2 H pluses for every hydrogen or water that you added. So to this side, we will add 14 H pluses to balance out the 14 hydrogens that we added a second ago. Any questions on that there? By the way, if you happen to be starting with a redox reaction where you have more hydrogens on one side than the other, you could just add some H pluses to the other side to balance it out as well. So you could just kind of use that to balance it. Once we balanced out everything, all the other elements, hydrogen, oxygen, the next thing that we want to balance out is the charge. And we're going to balance the charge by adding electrons. Now, the easiest way to do this is frankly the overall charge of everything on each side. That's because, as we just talked about, the overall charge is what all the oxidation numbers need to add up to anyway. So why reinvent it by going each element by element? It's kind of a waste of time because it's already done for you. And what I mean by that is a +3 on this side. That is a +2 on that side. Remember, we could only add negative electrons. That means I do need to add a negative electron to the right-hand side. That is going to give me a +2 on the right and a +2 on the left. The charges on each side do not have to equal 0. They just need to equal the same number on both sides. When I go to the bottom one, this is what I'm talking about. That is 14 positives. That is a -2. That is a net +12 happening over there on the left-hand side. On the right-hand side, that's 2 times 3, which is +6. And that is 0, which is a net +6 on that side. So to balance that out, we will have to add, we got there, that's 14, 12, there we go. 6 electrons will need to come over here. 6 electrons, which are now 6 negatives, gives me a +6 left over to match my +6 that's on that side. So again here, we could do that. So why is it important, for example, to know what is being oxidized, what is being reduced? We found out earlier that this is our oxidation half reaction. This is our reduction half reaction, which means when we add electrons to the oxidation, they should be on the product side, which they are. So that's good. And when we add it to our reduction, they should be on the reactant side. And that is good. They should never be on the same side. Otherwise, they will never cancel. And you screwed up. So that's a good thing to know, oxidation reduction. So you can make sure you added your electrons to the correct side. We're ready to add these back together. The one thing that we have to do, though, before we add them together is we need to make sure we have the same number of electrons in each of the half reactions. So I'm just going to kind of clean it up a little bit here. And as we can see here in the top half reaction, we have 1 electron. In the bottom one, we only have 6 in that case. So we do need to multiply this entire top one by 6. So I'm just going to rewrite it underneath. That'll give me 6 iron 2 goes to 6 iron 3 plus 6 electrons. Now we're ready to add. Electrons and electrons cancel. That leaves me 14 H pluses plus Cr2O7 2 minus plus 6 iron 2 go to 2 Cr3 plus 7 waters and 6 iron 3. If I did everything correct here, that should be balanced 2 ways. It should be balanced like a normal equation, which means you have the same number of elements on each side. That's 14 hydrogens, 2 chromiums on each side, 7 oxygens on each side, 6 iron on each side, and it should be balanced in charge as well. That's a plus 14. That's a minus 2. That's a plus 12. That's a lot. That's a plus 24, I think, on the left. That's a plus 6. That's a plus 18, which is a plus 24. So this would be balanced in acidic conditions. Any questions on that there? Yeah. How do I know to put these guys? Yeah, it is based on really the number of waters you added. So we're adding the waters here to balance out the oxygens, but because water has 2 hydrogens, right? We're also adding 14 hydrogens in this particular case. So if we don't put those 14 hydrogens on the other side, when we're all done here at the very end, we'll be short hydrogens over there. Yeah. Yeah, so we're basically just kind of adding the H pluses equal to the waters. So 2 H pluses for every water that you add. Other questions? All right, now let's say though that we wanted to do this in basic conditions. So if we wanted to do this in basic conditions, my recommendation would be do it in acidic conditions, just like we did. And at the very end, if you wanted to kind of turn this into a basic situation, all you have to do is take what you get at the end there. So we'll take that equation, which is 14 H pluses plus Cr2O7 2 minus plus 6 Fe2 plus goes to 2 Cr3 plus 7 waters and 6 iron 3s. And once you've balanced it in acidic conditions, if you want to do this for basic, you would add OH minus to both sides, and you would add it equal to the number of H pluses. So in this case, we would do 14 OH minuses here, and 14 OH minuses here. The side that has OH minus and H plus and OH minus make H2O. That will give you 14 H2Os that when they combine. You then can probably reduce down the H2Os. You got 7 on this side. If you subtract that from here, you will end with 7 waters on the left. Everything else will stay the same. And if I did not screw this up, I should now be balanced in basic conditions. We should still be balanced both ways. We have 14 hydrogens on the left, 14 on the right. 2 chromiums on the left, 2 on the right, 14 oxygens on the left, 14 on the right, and 6 irons on the left and right. Overall charge now is -2 and +12. That's like a +10. Over here is a +6, a +18. That's a lot there, and -14. So that's going to give me a +10 over here. So we are balanced in this case. Any questions on how to balance more difficult redox reactions using the sort of the water method here? By the way, out of curiosity, how do I know the top one is balanced in basic conditions and the bottom one is balanced in acid conditions? The top one is basic because there is hydroxide, right? Bottom one is acidic because there is H plus. That's how you know it's basically basic conditions are acidic conditions. Any questions on that there? All right. So hopefully that's a little review, I hope, of that stuff. Any questions? All right, I tell you what, why don't you, we won't do it now, we'll do it next time. Why don't you do at home and we'll go over it at the beginning next time. Why don't we do why don't you do that one at home and then we'll go through it next time at the beginning and you can just double check, make sure everybody's on the same page. This is this one here, balanced in basic conditions, okay? All right, we'll lay it up there for today.